So hello everyone. So my name is Olivier Grisel. I work at INRIA Saclay. I'm part of a team doing brain imaging analysis, basically for research on the brain. And in that team, my job is to work on projects, open source projects such as scikit-learn and JobLib. But today I'm gonna talk not too much about scikit-learn, but more about the more general ecosystem of Python to do predictive modeling, basically in Python, and present some trends and tools. So I don't know if you've seen, but a couple of say weeks or months ago, a data scientist from Los Angeles called Szilárd Pawka published a blog post where he took the results of the survey of the KDNuget blog that asked over the years 2006 to 2015 what was the biggest data set they used to do data science on it, to analyze. And so you have this cumulative distribution coming from in a logarithmic scale from 10 megabytes to 1 petabyte. And you can see that the median is approximately around couple of, it used to be a couple of gigabytes. And nowadays it's more like 20 to 50 megabytes or even more. No, yeah, it's 20 gigabytes. Approximately. So if you take the middle portion of that, of that graph, and you fit some linear line to the linear fraction of the graph, and you compare the slopes over the years, you see actually you compare the values. You see that you get a 20% increase year on year of the typical dataset size that data scientists tend to analyze. We'll remove the cursor. Okay. And comparatively, if you have a look at what was the biggest Amazon EC2 instance available in the cloud at around those same time, you can see that the size of the instances is growing much faster. It's 50% year on year. And nowadays we have available machines with 2 terabytes of RAM, approximately 2 terabytes on a single node. So you might think maybe over time there is no point in using a cluster, because anyway the big machines will catch up with the typical dataset size that we analyze. But so there is this Gary Burnett guy who tweeted this, as a consulting service, you bring to me your big data problems, and I say your data set fits in RAM, and then you pay me $10,000 for saving you $500,000. But maybe, there is some sample bias in that survey. And maybe people who reported to that website are regular readers of that website, and that website emphasize tools that are easy to use and nice to use and very interactive, and maybe therefore focused on data scientists that don't do cluster analysis on a big compute infrastructure, and so emphasize the tools that are not able to deal with that big data set. Those big data sets. And typically, setting up a big data cluster requires a lot of sysadmin skills, and you actually need to pay for a sysadmin to set up the machines and make sure they work. Actually hosting it, just paying the electricity or renting it on the cloud, it can be very expensive. And furthermore, when you work on a cluster, you have cluster-induced latency, like the communication between the workers, that might make the analysis less fun because of the latency, and less productive than you would do on a single machine. So Oh, sorry, there is a problem with this remote control. So I will switch the slide here. So for today, the outline of this talk is to present some evolution of the predictive modeling tools, then speak a bit about how to do scaling out, which means scaling on several machines, using more hardware, several machines in parallel to do the analysis. And I will present quite a recent project called Dask Distributed that makes it possible to do that in Python. And finally, I will also speak a bit about in-database analytics using MPP system, massively parallel processing systems, which is some kind of alternative for this kind of scaling out. So first, the evolution of predictive modeling tools. So the typical pipeline or workflow to set up, to build a predictive model starts from a history of training data. And usually you have some kind of target variable or label that you're particularly interested in and you want to predict. And so you have some original representation of the data that you need to transform into some kind of numeric array, a feature vector, like columns in a database or in a spreadsheet with numerical numbers. And once you have this intermediate numerical representation of the original samples in the history of the data, you can feed it to a machine learning algorithm, which is some kind of mathematical entities that needs numeric numbers to work. And then it will output the predictive model. Once you have this predictive model, you can copy it on production machines. You can make copies on several machines to process new incoming data in parallel. And typically, you need to do the same kind of operation, like feature extraction, to feed it to the model. And but this time, you don't provide the label. The model will predict the most likely label, or if it's a categorical variable, or some numerical value that is kind of the expected value. So if your data set is very small and you want to build a simple model like linear regression, you can do all of this in Excel. You just select the columns and you fit a linear regression on that, and then you can apply it to a new set of records. But as soon as your data gets too big, you have to use other tools, and one of those tools could be Python or the R programming language, for instance. And it's kind of nice because you can use libraries like NumPy or Pandas to load the original data and to transform it into a numerical representation. So Pandas especially is very nice if you have like heterogeneous data that you need to join, align, and clean up. And then extract some numerical arrays that you can convert to NumPy arrays, for instance, to feed it to a machine learning library like scikit-learn that will do the mathematic part. All the feature extraction, you do it with Pandas, for instance, and the prediction and the modeling, you can do it in scikit-learn. If your data is very big, people tend to use, in the open source world, tools like Hive, which is a SQL engine on top of Hadoop that runs on a cluster. And with this SQL engine, you can run queries that will do the same kind of operation that you could have done using Pandas, even though sometimes it's less convenient. But you can do it, and generally what you get as an outcome is much smaller than the original representation of the data. Like for instance, if you start from a click log, you have atomic interaction of users with a web service, for instance, and your interest is detecting anomalies like frauders or security attacks or stuff like that. So you want to characterize the user activity. So you will group the clicks by session and then the sessions by users, if you have user IDs. And typically, you can go from billions of individual clicks to millions of users. And if once you have extracted features for users, you just have a 1 million record, for instance, then it's much smaller, it can fit in memory sometimes, and then you can use tools like scikit-learn in memory, for instance, to do the predictive modeling part. So in general, the feature extraction tends to work with bigger data than the downstream stuff. If you don't want to use Hadoop, you can also use hosted services like MPP, massively parallel processing databases like Redshift in Amazon, or there are also Google BigQuery in the Google Cloud. And there are also open source alternatives based on PostgreSQL or Impala, for instance. To do this feature engineering in SQL and then extract the results after the aggregation to feed it to scikit-learn. And finally, nowadays, Spark is gaining a lot of traction. And it's kind of a versatile framework that can do cluster computing, both for feature extraction, data transformation, ETL, and also predictive modeling to some extent, either directly in Spark using the MLlib library or using third-party libraries like H2O, for instance, that can work together with Spark. So I would like to step back a bit and see the global picture, the big picture. Or why do we need predictive models in the first place, and where does it fit in the typical organization architecture? So nowadays, many organizations that have deployed services, that could be web services with a website where you log in, or mobile apps, or sometimes even embedded device that have sensors that feed information about the user activity. They typically are organized this way. You start from the user-facing front end. It could be the mobile app or the sensors and so on. And all the users' interactions are collected and aggregated in a distributed event log that just makes sure that you have a hard drive copy of those events, and you can ship it very quickly by topic to the target application. And you typically have two lanes. The fast lane on the top, which is typically a distributed event stream processing system that will process those events and update a database that will serve updated application views, like user screens, to the users. So for instance, when you tweet it here, you have some like JSON or protocol buffer record that goes to the queue. And then sometimes you need to transform it to broadcast it to find what are the people who follow. And then store the updated views of the followers, so that when they refresh the page very quickly, in less than 1 second, they see the new tweet. And you also have this slow lane, which is more focused about long-term storage, like distributed storage, for instance, for archival purpose, tied to a distributed batch processing system. That makes it possible to compute a large aggregate on all the history of all the tweets, for instance. And sometimes you can extract a more structured representation of a slice of this archive in a SQL database to do analytics. And then you can typically do dashboards to drive the organization to get some insight on what's happening. And on this analytical database, you can typically extract views to train predictive models, for instance, for recommender systems, for fraud detection, churn forecasting, or all user activity modeling. And those models can be directly used by the analysts, for instance, for predicting fraud, or can also be deployed either by deploying the predictions themselves in the database that is used by the front-facing application, or sometimes even deployed as executable model in the live distributed event processing pipeline, so that when you have an event, you can categorize it as suspicious or not, for instance, and directly filter it before tweeting it, for instance. So you have these typical architectures, and over time, different generations of tools have emerged. So for instance, for the distributed queue system, Kafka is the most popular solution nowadays. It's an open source project from the Apache Software Foundation. And there are many other Apache projects like Storm for distributed event processing, Hadoop HDFS for the storage, distributed storage, Hadoop MapReduce and Hive, for instance, for batch processing. You can also, if you don't want to use a Hadoop cluster, you can use a cloud drive or a storage like Amazon S3 to do the backups, and use a SQL engine like Redshift to do the analytics query. Use some machine learning libraries that can work in memory or not for predictive modeling, and store the results in a distributed database that is very quick to read and write to for individual records, like Apache HBase. There is also this trend of Spark going everywhere, because Spark supports streaming operations, it supports batch operations, it supports a SQL engine, and also predictive modeling. And people who use Spark tend to use Cassandra better than HBase for some reason. I don't know why. And Kafka, there is not so much competition on this side. Anyway, and the HDFS is still used even if you use Spark. So now I would like to speak more about how to scale predictive models. So why would you need to scale out predictive models? One reason will be for the I/O intensive feature enduring part, the first part of the diagram that I showed previously. And sometimes also, once you have trained a model, when you compute predictions, usually it's very fast to execute. It's much faster to execute the model, and you might be I/O bound, like the feature extraction layer part, retrieving all the information that are required to build the features, is limited by database access or file system access or in-memory access sometimes. And this is what is the limiting factor. And if you have more machines with more drives, more hard drives, then you can parallelize this processing and scale the I/O bottleneck. So this is typically the case where when you start from the original representation of like the click log that has billions of individual logs in several terabytes or hundreds of terabytes of data, out of which you extract session features by grouping and aggregating, and then user features by grouping and aggregating again, and sometimes filtering like the old stuff. And once you have this, you have a much smaller data set that can be processed in memory. Sometimes you want also to use several machines to benefit from more compute capabilities for the CPU or GPU intensive part. And so typically when you build predictive models, you need to constantly make sure that they work well by doing cross-validation. And also you need to tune the hyperparameters, so you need to fit many models with different values of the parameters and pick up the parameters that work. And some models like gradient boosting or random forest or large neural nets can be very expensive to train, and might benefit to use several CPUs on a cluster of machines or several GPUs on a cluster of machines just to train one single model. So it's good to keep the two needs as distinct because they don't occur at the same time. So, oops, sorry. Okay, I missed the slide. Okay, anyway. So many people use Spark, and it works really well, especially if you use it in Scala. But if you're more like a Python data scientist, you have to use a layer to speak to Spark, which is called PySpark. That makes it possible to run arbitrary code on a Spark cluster, Python code on our Spark cluster. But it adds some complexity by the fact that it mixes Python and Scala or JVM runtimes and to have them work together. For instance, you have this communication induced latencies between the different modules. Yeah, so you have a client-side Python driver where the data scientists write the code that will ship some function to a Scala engine that runs on the cluster that manage Python workers throughout the clusters and will ship the code to run on the workers and pointers to the data and get back the results. And actually, it's not pointers to the data; it's actually a copy of the data because typically the data is in memory in the JVM, and you need to serialize it and deserialize it in the Python memory to be able to actually execute your Python function on that. So this induces a lot of overhead. Some of that is going to be fixed at some point because both Scala developers and Python developers are working on that problem. But you still have this complexity of having Python to speak to Scala, then speak back to Python. So when you have an error, an exception, an uncaught exception, and you want to debug your Python function, for instance, you have a complex traceback mixed with a Scala struct trace. And to really understand what's happening, especially if you have memory management issues, you need to understand the whole stack, and that's more complex than just managing Python. And especially if you want to debug in local mode, there is, I think, maybe there is one for test, but it's not really advertised. There is no good pure Python local mode for PySpark that would make it possible to use the Python debugger directly or the Python profiler to run the same program without modifying it on a fraction of the data locally to debug it before using the cluster. So, as an alternative to PySpark, there is a more recent project developed by Matthew Rocklin at Continuum Analytics, which is called Dask Distributed, that provides several ways to do parallel computation and also out-of-core computation using collection-oriented APIs like bag, arrays, and data frame that are under the hood based on NumPy arrays and pandas data frames. But it just provides a logical view to aggregate several NumPy arrays that are chunks of data, basically, that can live in memory on a cluster or sometimes be stored on disk and transparently load it in memory when you need it. And furthermore, it also provides a more programmatic API where you have this Dask delayed operator that is kind of similar to the joblib delayed function. If you know joblib, and there will be a talk on joblib later today, I think. But it's kind of more general because it makes it possible to chain operations and to have a compute graph of dependent functions where the result of one evaluation is fed as in the input of many other operations, for instance. And once you compute this graph of compute operation, you can schedule it on a cluster using some kind of extension to distributed, which is called Dask Distributed. And that makes it possible to ship the data of the cluster, to ship the code that you need to run on the worker on the cluster, and to process stuff in parallel. So the second part is optional. You can only use a single machine if you want, using threads or Python process. But it can benefit from a cluster. So I will show you a video of a demo. Okay, so this is a IPython notebook running on a Google Cloud cluster using Kubernetes and Docker, if you know about those technologies. And basically, you have one server at a given IP address that hosts the notebook application, the Jupyter notebook application, and one other server that runs the Dask Distributed scheduler, where you see the state of the whole cluster. There are, like, I think in that case, 3 nodes. And each of them has 32 CPUs. And here you see the aggregate resource usage of the cluster. So you see that nothing is happening at the moment. And here you have some kind of summary view. It's very small, where you see that there are 3 nodes, 3 worker nodes, and each of them have 32 cores. And those are very recent as well. It's not very recent, but it's very good compute CPUs. So when you go back to the notebook, you can import distributed and open an executor process, which follow the same kind of API that the concurrent future executor API of Python 3, if you know. But you can also access. You can connect it to the cluster, and you can see that you have 96 cores on that cluster running on 3 different Python processes. So first, I will just install some libraries using a Python function that will call into via a sub-process called conda install to install dependencies. And I run that on the cluster on the 3 different workers using the e.run function. So once everything is installed, I will do some machine learning predictive models. So I will just use a toy dataset for the example. So I will just use the digits dataset from scikit-learn. So it's a bunch of images, 8 by 8 gray level images that represent handwritten digits. So they are very pixelated because they are very low resolution, but they come from people actually writing numbers. And especially digits. And so here you see a 5, and if you change the index in the array, you can see, please. Okay, it's a shape 8 by 8, but if you see if you change the index, you see a different number. I will just skip a bit. Okay. So once we have this data set, we need to do a cross-validation to be able to evaluate our model. So we need to split the data into 2 subsets. So I will create a function that will be the first step, which is called load CV split, that will actually load the data from the hard drive using this function. In real life, you could connect to a database or to Amazon S3 to load the data at this point. And I will split it into 2 parts, the train part and the validation part, and keep 20% for validation and the remaining 80% for training. And you see that there is also a parameter which is called a random state that has an argument which is a split index. And this split index is meant to be an integer value that controls the randomness of the split. So if I pass the same integer over and over again, I will get the same result. But if I pass 3 different integers, like 0, 1, 2, I will get 3 different ways to do the cross-validation. Once I have this function, I will define the second one that will take as an input the output of one evaluation of the previous function, a CV split, and additionally a model class and a set of parameters. And I will evaluate, I will train a model on this data. So first I unpack the cross-validation data, the train and validation part. Then I create an instance of the model by passing the parameters to the constructor, and I fit it on the training part of the data. And when I do that, I also record the training time. I just time it and remember. And then I will compute both the training score and the validation score of that model on that cross-validation split. And then I record everything in just a regular Python dictionary. And I also hash the parameters so that later I can do a merge, a group by on that. Anyway, it's a technical detail. So once I have those 2 functions, what I can use is define a parameter grid that will define the possible values for my model. In that case, I use SVC, which is a support vector machine classifier. And it takes hyperparameters such as C to control the regularization of the model, and gamma to control the shape of the decision function of the model, which is a kernel model. So it's basically the size of the kernel bandwidth of the support vector machine. And I also have a hyperparameter that controls the tolerance level of the optimization routine of the model, of the algorithm. And for all of those parameters, I define ranges of possible values, so in a logarithmic scale, because I just know that those values need to be positive But the actual good values really depend on the data. So I go from 10 to the power minus 10 to 10 to the power 10, and I will take 1,000 possible steps on that scale, on that logarithmic scale, both for C and gamma. So it's a very wide scale with many individual possible values. And for the tolerance level, I just explore a more restricted subset because I know the kind of values that make sense. So once I have this grid of parameter, I can embed those in an object which is called a class, which is called a parameter sampler from scikit-learn. That takes the dictionary of possible values as an input and take a second argument, which is the number of combinations that I will randomly select from that space. I will pick up one random value for C, one random value for gamma, and one random value for tolerance. I will have one combination. And we'll do that 3 times. And I will do that repeatedly for 2 cross-validation splits using my loadCV function. And then I will do the cross product of those 3 parameter combinations times 2 cross-validation splits using a traditional list comprehension in Python. So this is basically randomized parameter search implemented in 10 lines of Python. In scikit-learn, there is also a randomized search CV function class that does pretty much the same. But I just wanted to show that it's really easy to write it directly in Python. So here I just forgot to evaluate the previous cell, so I will just do it now. Okay, as usual. And now I have my function. So this takes some time, like 4 seconds, to do 5 evaluations because I have 2 cross-validation split times 3 parameter combination. So as I have a list of dictionaries as an output, I can load it in the pandas data frame and see the results. So the first column is the parameters, then I have this cross-validation split index, and then the training score, validation score, and training time. So here you see that many validation scores are very poor at less than 10%, which is approximately the chance level. If you make a constant prediction, like it's always 0 for my digit, you will get this score. So it's really bad. But the train score can go up to 100%. So it can also overfit and remember the data perfectly if it wants. So because it's too slow to run that on a single machine, I will use my cluster. So I will just connect back to the cluster, so it's still running. I will use the executor again to connect to it, and I will restart it just to make sure that everything is fine. And I have 96 cores. So instead of doing 5 iterations, I will do number of cores times 10. So approximately 1,000 parameter combination out of all the possible parameter combinations, and I will do a 3-fold cross-validation instead of 2 as done previously. So you see that the code is exactly the same, but this time I imported Dask delayed and I decorated the 2 functions with delayed. And you see the result of the first function is fed into the second function. And when you do that, basically when you execute it, it will compute all the possible steps that it will have to evaluate, but it will not compute the actual function. So you get as a result a delayed object that is just a pointer to the computation that has to be done on the cluster. And then you can pass this list of function evaluation to the cluster, the compute function of the executor. And there you will get a futures object that will give you a pointer on whether the function has been completed or not. And so once you do that, it's asynchronous, so you can still use your IPython notebook and see in the background that the cluster is being used. And here you can see that there is no white between the tasks, so all the workers are used 100% of the time, so the total CPU usage is very close to 100%. And while it's still computing, I can start to gather the results of what has been achieved, what has been completed so far. So if I execute this, you can see that I already have good results because one of the top performer is already 99% accuracy on the validation set, so it's very good already. You don't need to wait till the end to see that you already have good values. When I did execute that cell, I had half of the evaluations that were completed. You see that most of the 65% of the evaluated models are below chance level, are at chance level. So it's most of them are actually useless, but at least around 50% of them are also very good on the training set, which means that they are overfitting. And now we see that the computation has finished. So I can re-execute that cell to collect all the results. And you see now on the first line, on the count line, that I have my 2,880 results. Here I just do a histogram of the validation score, and you see that you have a bimodal distribution where most of the models are poor around chance level. And there is a group of good models to varying degrees and a few models in between. So before going further, I need to aggregate the training score, the validation score, and the training time through the cross-validation split. So I will join on the parameter hash. So for a specific combination of parameters, I will compute the average over the cross-validation folds for the training score. So it's just using regular pandas merge and aggregation. And I will sort by validation score and extract the top 10 models. And you see that they have a validation score that is very close to, that is more than 99% for all the top 10. And I also extracted the Python dictionaries with the parameters and unnest them into columns in the data frame. And you see that here the gamma values are very very similar to one another. So they are quite on the scale that I chose. They are all on the same region. Whereas for the C values, you can see that the orders of magnitude are changing quite a bit. So apparently the C hyperparameter is not that important, but the gamma value needs to be in that region to work well. And there is one exception here, but all of the others are very close to one another. And you see that the tolerance level is not that important. It needs to be strict enough, but it's not that important. So I can do a scatter plot of the validation score against the two parameters on the logarithmic scale, so C and gamma. And you see as a color scale the validation score, the validation accuracy. And you see that there is a large purple or blue region here where the models are really bad. They are around 10% accuracy. And a yellow region where the models are very good. And the red dots, they are red, are the top 10 models. And actually, if I do the same analysis for a longer period, you would see that the top 10s are all on the line here. So apparently, the value of gamma is very important to be in that region, so to be low enough, and you need to have C to be big enough also to be in that quadrant, basically. And once you are in that quadrant, you have a good model. So this is specific to support vector machines, but it's interesting. To dig further, we can also compare the training score to the validation score. No, actually, this is just the training score. And you see that all the good models from the training point of view are in that half. And you see that we have a region here that is different. So we can compute the difference between training score and validation score. And so you see that here you have almost 90% difference in accuracy between the training accuracy and validation accuracy. So this means that we have a large gap in that region, which is basically the signature of overfitting models. And finally, in that region that is blue, even on the training set, it's basically underfitting models. So by doing this map, you can really understand the behavior of the model. So I will skip a bit to the end. Yeah, this is the training time. We have the same kind of stuff, but we are short on time. So what is also interesting with Dask is that we can use the same Dask delayed evaluation to compute them locally on a single machine using Python threads. Because this is using scikit-learn and we release the GIL in most of the compute-intensive operations, using Python thread in that case is very efficient, and there is no memory copy. If you see that doing 10 evaluation takes approximately 1 second on a single machine using 32 cores. What is interesting with Dask is that you can remove the parallelism and run it into a single thread in the main process, and you see that we have 6 seconds, which is the user time of the previous operation, so there is very little overhead of parallelism. But now we can control that it's actually running on a sequential mode. So in JobLib, you can also do this kind of scaling down to a single Python thread and single Python process. And once you have this, it's very interesting because you can do debugging using PDB, for instance. There is no more parallelism. Exactly the same code, you can put it in sequential mode on a subset of the computation and actually debug it or even profile it. So here I'm using the prun magic from IPython notebook. And you can see that it takes 6 seconds. And then I have the profiling report. And you can see that most of the time is spent in scikit-learn libsvm, which is the C++ library for support vector machine that scikit-learn wraps. And the second most compute-intensive function is the prediction of the model. And then you see the third is actually numerical conversions between the original representation, which is integers for the data set, and it takes 100 milliseconds. So in that case, converting the data is not negligible. But it's very interesting to be able to do this kind of analysis because sometimes actually accessing the data is what is blocking you, and if you have access to a profiler very easily, you can see it very quickly. So this is what I like with using pure Python tools like that, is that you can use your actual profiling or debugging tools as usual by just switching to sequential mode. All right, we stop the demo. Switch back to the slides. Why, I can do it this way. Okay. So that was the demo. There are some limitations for Dask Distributed. So it's still a very young project, still under very active development. There was a release 0.10 yesterday. And there is one release every month, basically. So it's still the beginning. So the API is kind of stable, but I wouldn't rely too much on it. So it's good for evaluation right now, but maybe not necessarily for production, at least if you have a large team of developers. And what you have to know is that the kind of features that you have in a Dask data frame is a subset of the features that you have in a typical Pandas data frame. And PySpark also has a data frame API that is very rich. And especially until very recently, until yesterday, there were no distributed shuffle, which is very important, and that Spark does it really efficiently to do distributed merge and distributed group by and aggregate, so on a cluster. This was implemented very recently, and it's kind of the first experimental implementation of that. So it's probably not as efficient as the one in Spark or in Hadoop, but it's moving very quickly. So we can hope that soon enough, Dask Distributed would be a kind of generic alternative to PySpark that is pure Python. Finally, I also want to say a couple of words about an alternative approach, which is to benefit from an existing SQL database, MPP database, and to better use them from Python. So MPP databases are typically Amazon Redshift, Google BigQuery. There is also in the cloud IBM Bluemix. There are like distributed service for running analytic SQL queries. And if you would prefer to host your own open source analytic database, you can use Apache Impala or Citus Data, which is some kind of cluster version of PostgreSQL with column storage, and that is very efficient for analytics queries. And also, a couple of years ago, Facebook open sourced PrestoDB, which is also an alternative to those. And you could also use Spark SQL or Hive on Tez, which is another SQL engine that runs on top of Hadoop, but more efficiently than using the traditional MapReduce approach. So basically, all of those engines can run distributed SQL queries. So it's great because many data analysts are very comfortable with SQL and they can run Hadoop queries very quickly. But when you do data science, you want to visualize your data, and depending on the user interface that you use, it's not necessarily easy to do a matplotlib plot of the result of the SQL database query. And so what you could do is execute your SQL queries from a Python script that will then use matplotlib or bokeh or some visualization library, or build a model out of that. But then you have to manage SQL strings with parameters in Python, and it's kind of hard to maintain. It's not easy to write tests, to put in CI, and the traditional object relational mappers of web developers is not really a solution, because those solutions like SQL Alchemy or the Django object mapper is more focused about retrieving a single record to map it into a Python object, to modify it and to save it back. Here, in that case, we don't want to manipulate individual records. We want to manipulate groups of records to group by, filter, aggregate, using a Python high-level programming interface. So to do that, you can use one of those two projects, which are still under development. But I know people are already using it in production, especially Blaze, and IBIS is more recent. So Blaze is developed by Continuum Analytics and IBIS by Cloudera, by Wes McKinney, the developer of Pandas. And they both provide some kind of data frame API on top of a SQL engine, basically. So you have a Python program locally that will provide you a view on a table, some kind of thing that looks like a data frame, but when you run group by on that, it will do nothing until you do execute. And when you do execute, it will actually run the query on the database and either store the results in a new table in the database or retrieve the top 10 or top couple of thousands back to a local pandas data frame in your Python program. If you want to do visualization on aggregation results, for instance. You have to keep in mind that Blaze is more generic than IBIS, so it's not restricted to SQL engines. So in particular, it supports MongoDB and PySpark and other engines. So maybe it's less SQL optimized in a way than IBIS tends to be. And IBIS focuses on Impala right now, and also has some support for Postgres. So if you want to see how it feels, so you import Blaze, for instance. With IBIS, it's very similar. You point it to a database and a specific table in that database, and then you get an object. And if you display it, you see the top 4 rows in that case, with the different columns, and you have the type information that comes directly from the SQL engine that is used to see the Python view, to generate the Python view. And so you have categorical data mixed with numerical data in some kind of data frame, basically. And then you can do aggregation operations using Blaze by on the species column and compute those two operations for aggregation, min and max on the petal length. So on this column. And you see that the result of the aggregation is another kind of table lookalike object. So that's it for my presentation. So just to wrap up, I would like to say that so the kind of dirty secret of data science is that you need to tweak your models and your data to change stuff, features or parameters, to see how you can improve your model and to actually get insight from the data. And this seeing what happens is very important. So you need to have a conversation discussion with your data and your models. And because of that, you need a high level of interactivity. And once the picture is ready, okay. So this is kind of the secret sauce of the success for Python in data science, and also the R programming language, which is even more used, I think, than Python in data science. And this kind of iterative exploration, tightly linked with the visualization tools, is very important to get insight from the data. And the fact that this discussion happens at a low latency if you use a single host in-memory computing device, like a big server, makes it very pleasant. And because you can ask quickly a question and quickly get an answer, you're not afraid of asking the question in the first place. And you discover stuff that you would have ignored if you were too lazy to wait for running a cluster or something. So I think this is very important. And also the additional benefits of having a single machine installation is that you don't need a sysadmin. Usually it's quite easy. It could be improved, but it's still quite easy to install a data science environment in Python or R. Whereas installing a Hadoop cluster or provisioning a Hadoop cloud somewhere it takes more skills. It's not very difficult, but it takes more time to teach and to use. And because of that, those two ecosystems have a rich number of libraries that makes it very efficient to use those. So in conclusion, we see that the PyData ecosystem has many different initiatives to scale it, to be able to use more big data or big compute. It's still not as complete as other stuff like Spark, but I think it's going in a good direction. But when we go in that direction, I think what is very important is not to sacrifice usability on a single host. We should not have the complexity of a cluster on a single host to work. So I think it's very good to have frameworks like Dask or even the TensorFlow library or Ibis or Blaze or also JobLib that will be presented later today, that have this ability to switch back to sequential mode very easily to debug and profile your code. Thank you very much. I would like just to thank you Rackspace and Google for they provided credits for building the demo on clusters, and Enria, my employer, for my work on scikit-learn.